In this topic, we will look at sequences. Pause the slide now and consider if you can find the rule for each of these sequences and then determine what the next two terms will be. So the first sequence, you may have noticed that the difference between the terms is doubling each time, or you may have found another rule. Following this pattern gives us the next two terms, 78 and 158. For sequence 2, you may have noticed that the difference each time is halving, so it's going down by 26, then down by 13, and so on. Again, you may have found another rule, which we'll look at in a minute. This gives us the next two terms here. You may have noticed with sequence 3 that the difference between the terms is tripling each time, or again, you may have found another rule. The next two terms are therefore here. Sequence 4, you may have noticed that the difference between the terms each time is halving. And the final one looks slightly different to the others, but you may have noticed that the terms are alternating. And therefore, the pattern would continue like this. So if a sequence is generated by using the previous term to find the next term, we call this a recurrence relation. We'll return to the sequences on the previous slide in a minute to see whether this can be applied here. We use the term un to describe any term in the sequence. Therefore, if we want the next term along, we would call this un plus 1. If a sequence is a recurrence relation, where we are using a term to find the next term, we can write this using un and un plus 1 in a formula. So for example, if we took this sequence here, by considering the terms, you may notice that we can find the next term by doubling the previous term and then adding 1. For example, 5 multiplied by 2 is 10, add 1 gives us the next term 11. 11 multiplied by 2 is 22, adding 1 gives us 23, and so on. We could write this using a recurrence relation as un plus 1 equals 2un plus 1. What this means is that to get the next term in the sequence, this is double the previous term, so 2un, and then adding 1 onto the answer. So we're now going to return to the sequences that we considered a minute ago and see whether we can find a recurrence relation, see if we can find a rule that takes you from one term to the next term each time. So, for example, you may notice that the first one can also be found by multiplying a term by 2 and then adding 2 to get to the next term. For example, 3 times 2 is 6, plus 2 is 8, and so on. So this can be written using the recurrence relation un plus 1 equals 2 times un plus 2. Pause the slide and consider whether you can do the same for each of the others. So the second sequence, one possible recurrence relation could be un plus 1 equals un minus 12 all divided by 2. Similarly, you may have calculated this as a half un minus 6. This would give the same rule. The third one, you may notice that each subsequent term is found by multiplying the previous one by 3 and then subtracting 5. For the fourth sequence, you may notice that if we divide by 2 and add 10 each time, so we get un plus 1 is a half un plus 10. And the last one is a little bit tricky, but as you can see, you may consider that if you find 1 over 5, you get 0.2, and if you get 1 over 0.2, this gives us 5. So taking the reciprocal each time, and also adding a negative to take into account the fact that it is alternating plus and minus, we could use un plus 1 is minus 1 over un. For example, minus 1 over 5 is minus 0.2, and then minus 1 over minus 0.2 takes us back to 5. These sequences are called increasing sequences. This is because for every term, un plus 1 is always bigger than un. In other words, each term is always bigger than the one before it. These sequences are decreasing because for every term, the next term is always smaller than the one before it. So for example, un plus 1 is always less than un. This sequence at the end is called a periodic sequence because the terms keep repeating. How often the terms repeat is called the order of this periodic sequence. So for example, this one has order 2 because it repeats itself after every 2 terms. We're now going to consider a slightly longer example. Here we are given a sequence defined using a recurrence relation. Un plus 1 is a times un plus b. A and b are constants in this case. So we know that to find the next term in a sequence, we always take the previous term, multiply by a constant a, and add a constant b. We need to work out what a and b are, and we are given the first 3 terms of the sequence in order to do this. So first of all, we're going to start by writing out algebraically what the first few terms would be. So for example, we know that the second term, u2, will be a times the first term, u1 plus b. So u2 will be a times u1 plus b. Similarly, we know the third term will be a times the second term plus b. So u3 equals a times u2 plus b. We could continue this for as many terms as we like, but we have the values for u1, u2 and u3, so we can now substitute these in. So the first one becomes 150 equals a times 200 plus b, using the fact that u1 is 200 and u2 is 150 from the question. We can then substitute in u3 and u2 into the second equation. This gives us 120 equals a times 150 plus b. We now have simultaneous equations, so you can either put this in the simultaneous equation solver in your calculator, or because it's quite a simple pair of equations, you can just write one above the other and subtract to cancel out the b's. This leaves us with 30 equals 50a, so we get a value of a of 0.6, and therefore substituting that back in gives us a value of b of 30. It's always worth at this point checking that this value of a and b actually do work in the sequence. In other words, if we take a term, multiply it by 0.6 and add 30, does it always give us the next term in the sequence? We can now use these values to calculate u4. So we know that u4 will be 0.6 times u3 plus 30. So therefore, u4 will come out as 102. Now for part B, we want to find the limit of the terms as n tends to infinity. In other words, if we continued calculating the terms for a very long time, these terms would tend towards a particular value. We want to know what that value is. You could just calculate a lot of terms and see what they appear to be tending towards. In fact, you can actually use the recurrence function on the calculator. We'll do that in a second. But algebraically, we can say, well, if these terms are all getting closer to a value L, we will eventually reach a point where all of the terms are very close to this value L. So we can replace un and un plus 1 with the letter L. So therefore, as we get a long way down the sequence, we will approximately have the situation where L is equal to 0.6L plus 30. We have just replaced the un and the un plus 1 in the original recurrence relation with the letter L. solving this to get to the value of L. So if we subtract 0.6L from both sides, and then this will give us 0.4L equals 30. We can then divide by 0.4. This gives us 75. We can check this using the recurrence function on the calculator. We do this by starting with the first term, which we know is 200. So type 200 into your calculator, then press equals. By doing this, this will save 200 as the last answer registered in your calculator. So just 200 equals, just save 200 as an answer. You're now going to put the recurrence relation in. You're going to press 0.6 and then use the ANS, the answer button, next to the equals button. So 0.6 answer plus 30. What this will do is it will take the previous answer from the calculator, multiply it by 0.6 and add 30. Now because we saved 200 as our previous answer, when we press equals, it should give us 150 as the next answer. If you then keep pressing equals, it will keep substituting the last answer into that function. So we get 120, 102, and if you keep pressing equals a lot of times, eventually those terms will get closer and closer to the limit we calculated, which is 75. This shouldn't be used as the method for calculating the limit, it's just a good way of checking whether your value seems to be right. This tells us that this sequence approaches but never quite reaches a value of 75. Now complete exercise 1.2 on page 292.